Here we are on exponentials, page 16, and yet again we have another biology problem. These exponential functions are frequently the solutions to biological population modeling problems or bacteria problems, because the way living things usually expand in population is an exponential function, because exponential functions have a growth rate that is related to how many people or how many bacteria or how many bears there are. So it's very natural for the solution to these equations to be exponential functions. The more people you have, the faster it grows. Okay, a species of bear is introduced to a large island off Alaska where previously there were no bears. 6 pairs of bears were introduced in 1998. It's expected that the population will increase according to this function, which is an exponential function, where t is the time since the introduction. Find b subscript 0, which is the initial population, of course, because the multiplier that times the exponential expression is the initial population. Find the expected bear population in 2018. Find the expected percentage increase from 2008 to 2018. So you could consider the population to be 6 as 6 pairs, or you could put 12 because it's 6 pairs of bears is 12. So let's put 12. So I'm going to say 12 bears for b subscript 0. And then it says to find the expected bear population in 2018. We're starting in 1998, and the expected bear population in 2018 is 20 years later. So let's consider 1998 to be t equals 0, and then we'll consider 2008 to be t equals 20. And then it says to find the expected percentage increase from 2008 to 2018. And we have a space to draw a graph here, but you don't need to draw the graph. They never asked us for the graph, and we can use the calculator and just use the table to get this data, so we'll do that, okay? So we know that the function looks like this, and instead of b subscript 0, we're going to insert 12 because that's the initial population. So we're going to go to y equals, and we're going to clear it, and then we're going to put in the function 12 times 2 to the 0.18t. And instead of t, we're going to put x because the calculator only has x. I'm going to go to second table, and it's going to give me the number of bears each year. So in t equals 0, or 1998, the bear population is 12 because there were 6 pairs of bears, and it asks us for the bear population in 2018. That would be in year 20. 2018 is 20 years after 1998, and so it says 145.51. Let's say we're going to round it up because it's slightly above 0.5. So we're going to say there are 146 bears in 2018. And then it says to find the expected percentage increase from 2008 to 2018. So remember, with percentage increase, in the denominator, you're going to make a fraction. In the denominator of the fraction, you're going to put the original amount, which was 12 bears. In the numerator, you're going to put the amount of the increase. So we know that the new amount is 146. The old amount is 12, so the amount of increase is 134. So we're going to put the amount of increase in the numerator. And so 134 divided by 12, so let's do that on our calculator, is going to be 11.16 times increase. So we're going to multiply that times 100 to give us a percentage increase. So our increase is 1,116 or 1,117%. It's a huge amount, right? But that makes sense. We started with 12 bears. 146 bears instead of 12 bears is many times more than 100%, right? Okay, let's go to number 4. The speed v of t of a chemical reaction is given by v of t equals v subscript 0 times 2 to the 0.05 t, where t is the temperature in degrees Celsius. Find the reaction speed at 0 degrees C and at 20 degrees C. So we have a equation, and we know that the T here is the temperature, okay? And so if we're finding the reaction speed at 0 degrees C, we're going to put 0 in for T, and that makes this part of the equation into a 1. And so then we know that V0 is the reaction speed, okay? And we don't know what V0 is, so we're just going to say that the reaction speed is V0. Then at 20 degrees, we're going to have a different reaction speed. We're going to put 20 in for T, and we're going to get V subscript T is equal to V subscript 0 times 2 to the 0.05 times 20. 0.05 times 20, if you do it in your calculator, you find out it equals 1. So actually it's 2 to the first, okay? So at 20 degrees, V subscript T is equal to 2 times the speed of the chemical reaction at 0 degrees. Okay, so at 20 degrees, the speed is twice the speed of the original speed. Find the percentage increase in reaction speed at 20 degrees compared with 0 degrees C. Okay. Again, in the denominator, you're going to have the original speed, which is V0. In the numerator, you are going to have the increase in speed. So you're going to have the new speed, which is 2V0. You're going to subtract the old speed, which is V0. Guess what? 2V0 minus V0 is going to give you 1V0. So you're going to have the increase, which is V0, the original amount, which is V0. So the amount of increase is going to be 1 times 100 per percent, and you're going to find out that the increase is 100% increase. Okay, when you say there's 100% increase, you're doubling the original amount. Last of all, we're going to do part C. We're going to find V50 minus V20 and divide by V20 and multiply by 100%, and we're going to explain what this calculation means. Well, remember, when the denominator is a certain amount, that's kind of what we consider the original amount. And then the difference between the original amount and the new amount, like V50 minus V20, that is an increase, okay? So this is basically, we're talking about percentage increase just like in B, except instead of a comparison of 20 degrees C reaction speed with 0 degrees C reaction speed, now we're talking about a comparison of the 50-degree reaction speed compared to the 20-degree reaction speed. So basically, it's the same thing as B, but it's a little bit different. We're going to write the percentage increase in reaction speed at 50 degrees compared with 20 degrees. Okay, so that's it.